you got in there? You've got metals and you've got hydrocarbon-based plastics, right?
Good question. Let's go through the classes of fuel cells from high temperature to low temperature and see what they're consisting of by bill of materials. Starting at 1,000 degrees C, which is how many degrees F? Yeah, that's right.
Well, use that other red marker. It shows up a lot better.
Does it? Okay. Starting at 1,000 degrees C, you get around to a class of fuel cells that usually opt to conduct the oxidant or oxidizer towards the other side, towards the metal. And in that regard, you're usually faced with the need to have a type of bill of materials that uses zirconia, doped zirconia. And again, I'll put this on plate type configuration. So you have a fuel, which might be natural gas, and a supply of oxidant, which might be air, and you diffuse the oxidant as an ion towards the fuel, which gives electrons for the load where you do work, or to the inverter where you send it on the grid.
So you're drawing two plates there?
Yeah, this is, I'm gonna spread this out some. So we have two plates. On the air side, our job is to reject nitrogen, convert oxygen to ions, transport them in the zirconia, ZrO2, and you might have yttrium with it as an example of what's in the bill of materials. And it goes to a junction where you take it from high temperature to low temperature and get into aluminum or copper for cheap conduction. So you have something up here that stands the temperature at 1,000 degrees C that is also a good electron conductor. And then it goes into copper or aluminum to get on the grid.
So the nitrogen bounces back, it doesn't go.
That's right. So the nitrogen is rejected. Remember, our semi-permeable membrane is always going to do the same thing. It's going to let no electrons in. It's a good electron block. But it's going to welcome ions. In this case, it's going to welcome oxygen, for example, using air as the oxidant, or oxygen as the oxidant.
The elements that we're looking at here?
Oh, yes, we have zirconium. This electrolyte in here is going to be zirconium and yttrium. But mostly zirconium, so I'll... Oh, I'm sorry.
Yeah, okay.
So the electrodes also have to stand, that is to say, getting those electrons out of there, have to stand high temperature.
That's a solid electrolyte then?
It's a solid electrolyte. This is a solid electrolyte. S is one of the letters used in the abbreviation oxide, SOE, or SOM, solid oxide membrane. But remember, this membrane has one important characteristic that's different than the ones we discussed earlier. This one's transporting oxygen ions towards the fuel.
What's the electrodes basically made of?
Well, what do you think we should make them of that would stand 1,000 degrees C? First of all, it has to not melt at 1,000 degrees C. Secondly, it mustn't oxidize and become an insulator. And furthermore, it should be cheap. On one electrode, you could probably use carbon because it's in a reducing atmosphere. It's the fuel side. The other one's going to be exposed to hot air. So you start looking at things like the silicon compounds that you can dope for the purpose. The trick here is to dope it so that it protects the zirconia, carries the electrons out, and what you try to use is a little bit of platinum group coating, as little as possible. or the refractory metals that are in combination with protective coatings. Please.
Now, the ions that are going into the electrolyte there, aren't they mostly protons?
Well, no, these are going to be big ones. These are oxygen ions.
Okay.
These are.
Electrons are much smaller than protons, right? So
That's true.
The electrons don't go through. I mean, how come the smaller stuff doesn't go through, but the bigger stuff does?
Oh.
It's contradictory.
But it seems contradictory. This is a very important point. The question was, how does this semi-permeable membrane know how to be semi and not conduct electrons as gleefully as it would protons, or as gleefully as it would these great big oxygen ions? It's the nature of matter. It's the nature of how you build it. And in this case, you build a matrix. You build a lattice that only has in it these things that need to be held as the lattice points are transported across the lattice points. And so you're taking oxygen off one side and adding it to the other. And in that gradient, it replenishes itself. It's like billiard balls going across a table in uniform way, in a uniform bumping off of one side and adding to the other. As another example, as another figure of comment, if you build the lattice out of zirconium and oxygen, other things don't fit and would be used up if they got there, such as electrons. If you add electrons, why, it changes the valence temporarily of the zirconium, but doesn't go anywhere. And then that zirconium is glad to give the electron that it's gained in its momentary change of valence to oxygen. It's glad, it's lower free energy for it to do that than it is to try to hand the electron across otherwise. So it turns out to be the lowest free energy, the lowest energy consuming step for it to make is to transport oxygen.
So really it's a matter of incompatibility rather than space.
It is incompatible. You make it an incompatible system.
So what's the byproduct of the cell?
Well, the oxygen gets across and makes a combination with the carbon and the hydrogen and makes water and carbon dioxide. You can get to the bottom line, so to speak, by determining the output voltage of a fuel cell. If you divide that by 1.48, you have the efficiency. And to the proposition that fuel cells are more efficient than piston engines, and they typically are because we've decided they had to be, but still, in all fairness, look at myth number 16, which appears in your it's in the Philosopher Mechanic, but it's also in this blue fuel cells.
What page?
It looks like it would be about page, if they were numbered, 3 or 4 rather, of the appendix. It's right across from typical fuel cells.
Hold that up.
Yeah, it's the one that looks like this in the appendix.
I'll probably end it there. I'm mixed up with these page numbers. I don't know.
Yeah, well, we'll can.
That's number 16?
Yeah, it's.
Third or fourth, unmarked. No,
That's right.
unmarked page.
It's right before how does this cell work?
I didn't know there were unmarked pages.
Yeah. So does everybody find the myth number 16?
Yeah.
Well, there's a widespread myth that fuel cells have to be 2 or 3 times more efficient than piston engines or gas turbines. They don't have to be. They are more efficient as they've been construed lately for purposes of going to the life support systems for space applications. But if you looked at why piston engines aren't more efficient, you can start to notice that they have the potential of being quite efficient. Illustratively, in analysis, if you look at the Carnot efficiency as a potential working between, for instance, 5,460 degrees Rankine or 5,000 F for your peak combustion And if you really insulated that combustion within excess air and started the expansion at that temperature and didn't lose heat and took it all the way to 400 degrees as the degree of expansion, you could look at an overall potential for efficiency at 84%. Piston engine. That's beyond the scope of today's materials and practices, but it's still a potential. And there are engines that get half that. There are engines, and basically there are two engines in combination. One is a piston engine, a diesel engine, working as the primary first user of the fuel. The second engine is a turbine in the exhaust. But instead of using it as a turbocharger, it's used directly to combine torque with the piston engine, or in a separate channel where you put the application of the turbine on a generator, electric generator, and add up the electricity produced with the generator and the shaft power produced by the diesel, and you can get over 40%. Such engines are sold commercially for marine and large stationary applications. The point is that in all fairness, and you know, it came up over lunch that I think that in all fairness we'll be the first to tell you that although fuel cells are hitting the market at higher efficiencies than piston engines have a ways to go if the industry chooses to take advantage and get into the 40% range. It brings up again this issue of efficiency. Efficiency is very important from the standpoint of any economic analysis that's going to be done. And referring now to page 127 in your text, or look after 127 to the next page, which is a diagram. In the diagram, if you were to mark this up to hydrogen-oxygen fuel cells, the theoretical voltage would be 1.48. The no-load voltage would be about 1 for room temperature hydrogen-oxygen PEM type fuel cells.
Hold on, on page 127, this is in the blue book.
Look one more. Excuse me. It's 127 and a half.
Okay.
It's the back side of 127. This is the other summary of the story of fuel cells. And in this diagram are a number of issues that we need to really pay attention to and understand if we're going to improve fuel cells. The theoretical voltage, again, is about 1.48 based on enthalpy. The no-load voltage is around 1 volt based on practical application of fuel cells. Where does it lose the 0.48 volts? Well, it's in activation energy, getting the hydrogen activated. And what that means is that the first thing you do to any fuel cell, such as this high temperature fuel cell or a low temperature fuel cell, is to get hydrogen chemically responsive to the presence of an oxidant and the conditions under which you start making that chain reaction sustainable. You can either do so with high temperature, as we do with this ignition, or you can do so by just, first of all, making the hydrogen very exposed. So you start with big hydrogen, in which you have a proton and a molecular size that's like this, and now you want to get it down to just the proton. To do so, it takes energy. You first have to give it energy to make it into atomic hydrogen. Then you have to give it more energy to get the electron off. Then it's ready to react. That's part of that voltage, that activation. If you're at the other extreme, this being the PEM, if you're at the other extreme and you're up here with a high temperature cell, such as this zirconia, solid oxide membrane, then you also need to incur the cost of heating it up and operating it at a high temperature. You know, still you have that activation going into the fuel, which started at room temperature. Now you use heat to bring it up to temperature to make it reactive. So it's consuming energy one place or another, either in voltage at low temperature or in heat units at high temperature. Between the two are shades of everything we've talked about, but they'll all of these fuel cells will fall in this type of listing of losses. You have those activation energies, and they continue. Even after you start carrying current, there's activation energy. Activation being sometimes in the literature referred to as chemical polarization. So that first voltage drop that comes down that's shown on the chart is something you incur from the type of fuel you use, the temperature of the cell, and the selection of the materials in the choice to have or not have, for instance, a catalyst to aid the reaction. In most of the low temperature cells, you do have a catalyst. Otherwise, the cell runs very, very slowly and produces a really small current, or never gets to a current because it uses up all of its potential internally. Catalysts in low temperature cells are virtually required. You can't do without them. If you would look at just that activation energy as it continues in the addition of current, if you start pulling more current out of it, you'd get this dotted line that's the top line. But there are more losses because when you really measure, it goes beyond that. If you count up, do the accounting on all of the activation energy, it isn't enough to account for the voltage drop that you actually see in the solid line. So then you start measuring. For instance, you reverse the polarity and measure the resistance, and you find that the resistance accounts for the lion's share of another big loss, of most of the loss that is shown in the voltage. Beyond activation is the internal resistance. The internal resistance is measured at a number of places. It starts at the places where you make junctions. Everywhere that there's a change of material, there's a change of properties and a measurable resistance. So getting the electrons out, getting the ions into the semi-permeable membrane are two major paths, and in the course of getting them there, you encounter individual resistances. You're trying to get a good electron path and no electrons in here. You're trying to get a triple phase event where you have simultaneously a fuel changing from a gaseous diatomic molecule to an ion, and the electron going away. And those surfaces are all subject to and produce measurable ohmic losses. In order to reduce the ohmic loss of the membrane, what you'd like to do is to make as thin a membrane as you can afford and still not get gaseous hydrogen across it, or whatever your fuel may be. You want to avoid the giving away of the potential energy to the oxidant by blocking anything but an ion that you produced.
So the thinner the membrane, the better you are.
Yeah, for ohmic losses, the thinner the membrane, the better you are. Then you balance that with how much you're willing to give up of diffusion exchange of molecular or atomic and not ionic substance. The only thing you want to go across there is ions. You want to carefully prevent any gaseous diatomic molecules or any other type of molecules or any atomic particles from getting across. The only thing that
When you start leaking them, does it just lower the efficiency of the fuel cell, or is it destructive to it?
it lowers the efficiency. It may produce so much heat that it ruins the fuel cell. I produced cells that I thought were going to be gee whiz good ones, and made the mistake in testing them and getting the pressure too high, forced the diffusion to the point that they changed the membrane. They lost conductivity. Which brings you to the development of adding pressure. If you plot voltages in a fuel cell, you'll see a condition that looks like this. There'll be a curve, and I'll put that as the lowest curve, and another curve of operation, and another curve of operation. And what this one will be, for instance, hydrogen with air, this curve. Hydrogen with ambient pressure air. This will be hydrogen with oxygen. No nitrogen in it. You'll get a better voltage than with air. This one will be I'm going to put the brackets on it just to tell you about it. It's going to be hydrogen at pressure and oxygen at pressure. The higher the pressure, the more you can retain this original voltage. But the more you induce diffusion in your semi-permeable membrane of the gas, and the more heat you're going to put up with, the more you jeopardize the system for producing heat that didn't turn into electricity. For most economic analysis, you'll find that the industry is looking at about a 30% efficient fuel cell on American numbers, that is, using enthalpy as the denominator, or using produced voltage as the numerator compared to 1.48 as the denominator. That means 70% of the energy that you put into the cell has to be taken away as heat. Or you start melting down something, or you change the operation internally if you have that heat build up that is the 70% that isn't going into electricity. Big numbers in terms of what you have to do in small spaces. Why that's important is that it figures prominently into the way you decide to arrange stacks of these to get a higher voltage, so you have smaller conductors carrying the current. The objective is always the same. Use common materials as cheap as possible to do the uncommon thing of keeping oxygen and fuel apart until they've done electrically what you desired for them to do, and that's produce current at the highest possible voltage. But in the compromise that you always trade, you say, well, what am I going to be willing to trade? It's usually efficiency instead of putting more platinum in. You say, I'll take a little lower efficiency at lower uses of platinum because that's pretty expensive. Or I'll take a little less efficiency at smaller electrolyte areas because the electrolyte turns out to be pretty expensive. Or I'll take lower efficiency because of the components that are besides the electrolyte and the electrode are very expensive. The flow separators so that you can stack these together turn out to be a pretty big expense. And then if you start looking at the cost of getting rid of heat, that's cheaper. So you just put in some plates and circulate them with water and carry away heat and incur a lower efficiency at a lower overall first cost of your device.
Even if you are only at internal combustion efficiency or a little bit above, you still have significant other advantages. Low maintenance, no moving parts.
Very true. You have a much simpler system in terms of subsystems as well. But let's look at subsystems before we pass on that, because they are needed. If you're running a semi-permeable polymer membrane, semi-permeable plastic membrane, and now we're again at the low temperature end of the possibilities of temperature categorized fuel cells. If you're running a room temperature, an 80 degrees C or 90 degrees C or less fuel cell, you're going to be using a perfluoroalkoxy sulfonated polymer that can't stand much more temperature before it starts losing the ionic capacity, ionic conduction capacity. But it likes to run at about 80 degrees C in order to have good diffusivity of the ions. It gets better up to that temperature and then suffers longevity. It suffers life problems at a much higher temperature. Point is, that polymer has to be kept at a certain moisture content. You need to provide humidified hydrogen to it. An important subsystem for this type of fuel cell is to supply this side with moisture so that the membrane doesn't dry up and crack and let hydrogen get through the cracks. And so that even before it would dry up and let hydrogen get in, so it doesn't lose this capacity for being a good conductor for ions. So you'll need a way to circulate the hydrogen. You need to input hydrogen and circulate the moisture so that you maintain a humidity that is adequate for the membrane purposes. That's a subsystem that usually consists of a pump, a gas pump, and a humidifier. The humidifier can be any of a number of different kinds. It can be a spray type, or it can be a wick type. It can be a lot of different apparatus, but you need to have that system if you're going to have a high-powered, dense energy source. Same way with the other side, you need conditioning that goes on the other electrode. This one is producing water as it reacts oxygen with the arriving membrane, with the arriving hydrogen ions in the membrane, and adds them to electrons that are coming from the external circuit. So what we have here is the load that we've applied. The electrons come over and must come to a place where they can find oxygen. And this arriving ion. And why that's very important is that if it just builds water up here, it'll block the oxygen or block the arriving ion. You have to arrange for it to not be there. You have to arrange for it to either be removed by dehumidifying the oxygen that gets there, so it'll take up some of it, and that only works for a little while. Or you have to circulate the oxygen up as the carrier to remove the water, or you have to use capillary action to divorce the water. The best selection is to have a system that is phobic of water, doesn't want water, that's always rejecting water. And this is why a Teflon-based membrane is quite helpful. It's a water rejector in that sense. Then you put places in it that are water electrolytes. And so now you have a system that is conducting these ions on the water electrolyte and divorcing water on the other side as it's producing it. That is an excellent arrangement, but it illustrates the concentration problem of buildup of the product, the water, and blocking the reactants, one or both. So you have this balance going on. You have water removal, water addition to maintain the integrity of the membrane, and you must maintain the integrity of the catalysts. These are typically platinum catalysts with no contamination, no buildup of carbonates or oil or anything out of the fuel supply that would blind them or chemically combine them so they couldn't react further in serving you as a catalyst. Please.
Is that fuel cell in the box there a good example of all those forces?
It is. This is the fuel cell that we're going to be putting together is an excellent example of all of these forces. It's built to perform most of these functions without the subsystem of a circulating pump. and can do so because we're going to use such a small area cell that the amount of heat that it can give up to the atmosphere is adequate to keep it from overheating. It, even with plastic, is able to maintain a temperature that's adequate to keep it from overheating. I'll pass this around. It'd be good if you just took a hold of it on one of these two electrodes. But you can get a good look at it and look inside and see these very features that we've been drawing on the board in planar descriptions. Please.
I've run that system for 2 to 5 hours, saved a clip and stored it for 3 weeks, and fired it up, and it starts right up again. And you know, in New Mexico, dry air. Yeah, that particular cell right there.
What Charles just described is that he made enough humidity that on the off time it was re-establishing the water balance in that cell. You need to run it often enough to keep that moist.
That's what I was wondering, yeah.
Yeah, the more,
Sit too long.
that's right, the more often you crank it up, the better.
Okay. I wondered what the balance was between wearing it out prematurely by doing that and wearing it out prematurely by not doing that.
No, it's much better to run it.
Okay.
Your enemy in this cell is dry out.
Okay. I store it with some water in the plastic bag.
Yeah.
Will that help?
That helps immensely. Is to,
Physically permanently damage the shell, the cell by letting this one dry out.
that's true. And the solution is to run it more often and to store it so that it has a supply of water in the bag. The more you run it, the better, except if you're ingesting impurities either in the air or in the hydrogen stream that would poison it. The type of impurities that can poison this cell are oil. If you're using oil compressors and delivering to it a compressed supply of oil-laden air, it'll run it. Or if you have a supply of hydrogen, for instance, that has oil in it for some reason, such as it might have been put through a compressor, that can run it. It runs it by running the catalyst. This system is very sensitive to the functionality of the catalyst. If the catalysts are blinded or
Calcium here.
platinum.
How is that moisture thing dealt with on these fuel cells? Not
It-
this one here, but
If we wanted to get a bigger application than what we have in this demonstrator, if we wanted to run, for instance, a camera or a television or a radio for your home, we'd build up a stack of these. We'd build up a system of units like this, unit cells like this, in series connection. So we would build a however many volts up that we wanted, such as a 12-volt system. We might have 20 or 30 unit cells like this, so that they could produce 12 volts at a current level that they were able to sustain that production. But that would bring into question, would we do it with what type of series? Would we just build every one like this and then electrically connect them in series, or would we like to make it more compact by what is known as bipolar arrangement? We'll make, in this bipolar arrangement, an anode, a semi-permeable membrane, a cathode, but we'll run one side of the cathode as the next anode. So we'll have a anode, a cathode, and on the other side of that very electrode, we'll make it into an anode. And across the way, we'll just do the opposite. We'll have it as a cathode here, and so forth, until we have added up the number of voltage units that meet our requirement, our entire load requirement.
Well, if you're stacking the cell in this manner to gain the voltage without having to physically connect them by
That's correct, by external connection. We're also making the case here that you can be very compact in terms of volume. And it turns out to be pretty well self-supporting. You can make this into units that are held in compression.
Flow of gas on there?
Well, the flow of gas,
This was an hydrogen and air cell.
this is a hydrogen air cell. The flow of gas would look like this. We'd build into this places for the hydrogen to be circulated, and similarly places for the air to be circulated on the other side of each of these flow plates. And the result is that this makes the occasion of bringing the hydrogen to this one and the oxygen to this one. And you might think of this as a spiral. If this was a circular disk, you might choose to have this on spiral geometry so that you'd feed it in here, it would disappear in the middle. It would feed all of the section, the area, and disappear in the middle. And you could do it either way. You could do it from the inside, and the next one you can make it from outside feed or central feed by your choice. But the key is that you would have a compact stack that you could put in compression and make sure that it didn't have a way for hydrogen to leak out, because you could form the gasketing right out of the system. But pretty soon you run into this question of where am I going to get rid of the heat? How's the excess heat going to be dissipated? So you wish that this thing would also be built with an internal water cooler. If you're really going to the nth degree of compaction, you'd build these systems up, this flow and electrode bipolar unit, also as the water heat sink. So you could immediately go to Jerry's application and say, hey, I can make your electricity and give you hot water or steam, which would be a very good thing. And you could then determine between the two of you what the best market was, the ratio of voltage, the number of cells that you stack up in the bipolar arrangement, and where the water goes to satisfy a water heating or laundry or space heating need.
I had submitted a proposal to the SBIR, Small Business Innovative Research, to take that excess heat and through a thermoelectric conversion, grab an additional. It wasn't a lot, but it was still electricity, and then
Right.
just add that to the system. But
Anything that you do to improve that use is good. I mean, that's the direction this has to go, is to put it into some purpose that avoids metered energy somewhere else. Please.
And in an automobile, would that be enough to accomplish your heating of the car and air conditioning?
Absolutely. Yeah, you could run, in round numbers, you could run 80-degree water out of this, which is very adequate to heat a car. 80 degree. How many Fahrenheits is that? Yeah, 80 degrees C would do very adequate. The answer is it's very adequate.
Well, for cooling.
And for cooling, you could run there are a number of cells you could run. One is a hydrogen hydride heat pump. Here's how it works. Glad you asked. There's a type of heat exchange system that's based on a first reservoir of hydride. You add hydrogen to it at ambient pressure or some low pressure. Then you close the valve or run it through a check valve and heat it up. You add 80-degree heat. It then gives you hydrogen at high pressure. You can produce 400 psi, one step, out of a silent hydride by cyclically adding the heat. So you turn on a valve to circulate the 80-degree water to this unit, and it drives off high-pressure hydrogen. You take that high-pressure hydrogen one of two routes. You take it through a small motor and get motive power out of it. You can run this through, for instance, a small turbine or a small piston expander and run it to low pressure and low temperature. The idea is that once this is expanded, it goes to a low temperature. You take that to a heat exchanger, run a fan across it, and cool the car.
What are you talking about? We're getting our cooling from the energy of expansion.
Yeah, the cooling is producing low temperature, which we use as a heat sink for cooling the air.
What's the turbine for?
So the turbine is for taking energy out of the high-pressure hydrogen and doing the expansion to low temperature.
So it's basically what we use now for expansion valve.
Expansion valve. Well, you could put an expansion valve in, but this is more recovering. This gets back more than just the expansion valve. You get the expansion, but you also get cooling, a heat sink for cooling as a result.
Do you know how much cooling we do in a normal passenger vehicle?
Yeah.
Big time.
Yeah, you have no latent heat of vaporization.
That's true.
Problem.
This one has no latent heat to deal with. This one isn't like expanding Freon.
Yeah.
This is a direct gas cycle.
So what do you, then the hydrogen comes back, you just let it expand and you let it reabsorb back into the container?
You can, yeah, well, you can put this hydrogen now goes to a alternate cell, an alternate hydride, which is in the out of phase condition of this one.
Right. You know how many BTUs an AC system has to give for a typical 4-passenger vehicle?
In Phoenix, on a hot day.
Yes. 350 BTUs a minute.
We can do it. The hydride heat pump can do it. The other part of this story, and I think it's an important part of the analysis, is that this is a way that you can marry, so to speak, a chemistry with what you're using. You can replenish hydrogen in this system if it happens to leak past a seal with your very source of fuel for your fuel cell. So it's compatible. It gives a smaller number, or you have fewer things to keep track of, no Freon in the system. There was another question. Who had the other question that I ignored for a moment? Gene?
Yeah, asking you how to get the electric out of the
Fuel cell.
fuel cell.
Well, the way you get the electricity out is each one of these is a voltage producer. The potential between here and here, it starts out at about a volt, goes down to a half a volt or so, maybe less. But every one of those is a series connection now. You just series connect them, so the electron that you start with over here comes out at this end, but at a voltage multiplied by the number of times you repeat the unit cell.
But stack size.
Or the stack, yeah, the stack size. The stack size is however many unit cells you put in it and add them up in series. Then after a while you decide, well, we probably ought to put some of these series units in parallel, which you do, and build up as much power as you decide for that car to have or for your home to have. Gene, does that get close to it for you?
Yeah, that answers it. Thank you. Thank you.
The main thing, though, is that you're always balancing this question of how much heat do you allow. Remember, heat is our choice. If we let everything happen that's going to happen, it'll try to get to heat. You know, if you just let nature take its course, it'll all go to heat. But what we're going to do is insert our apparatus and our designs at places that give us results that we need before we get the heat. Before we get down in availability, we're going to get as many things out of it as possible.
What was the heating temperature you're using on the hydride itself?
80 degrees C.
That's fine.
More is better, but that could work. If you go to a phosphoric acid, well, you have a much more efficient hydride heat pump. You can do a lot more.
Like about you use a higher temperature or a medium temperature fuel cell.
If you go to phosphoric acid at 200 degrees C, you've got a much more compact hydride heat pump.
Yeah, but your cold sink on this side is going to be 25 degrees C air.
That's true. That is true. The other comment to be made in that regard, and I think this is an important one, is that you can control the voltage drop by pressure. The higher the pressure, the less voltage drop. You can overcome some of these effects that are stealing voltage. We're still on this, on this graph, analyzing this graph. So increasing the pressure of the air would decrease these losses. Increasing the pressure of the hydrogen, which you'd like to do in conjunction with the air so you didn't have a pressure imbalance I should say, is what you would match with a higher air pressure to get a higher voltage. The slope on this curve wouldn't be as steep. If you use straight oxygen, it's better. Straight oxygen would give you a higher voltage or less steep drop-off on these polarization. Making sure that you don't build up water helps reduce the slope on that curve. So finally you get to this point, and you've done all those things, and still it isn't satisfactory in the voltage. And you start looking with a microscope at the problem, and you find that you're overloading the catalysts. The catalyst that is doing the job is heating, so to speak, because it has too many electrons going out of it towards the external circuit, too many ions going out of it to the internal circuit, and it's the bottleneck. And that's usually, in round numbers, that's where we put our money. We put more money in more catalyst. And that's true on the phosphoric acid as well. If you're not satisfied with the voltage you're getting at the current you're needing, add more catalyst. Or put the catalyst at a smarter place. In terms of improving the system, you can look by rule of thumb at three major opportunities. One is in the electrodes. The second one is in the cost of the membrane. Right under the electrodes is the membrane cost. The third is in this flow plate, the system that looks like an electrode to you because of the way you've doped it or the way you've stacked it. But these are expensive too. They're typically made of carbon or graphite. And they become more complicated every year because somebody does more by way of making a heat addition to start them up, a heat subtraction to keep them from overheating at high amperage, and they become more complicated to build. By now they're building them in two halves within which there's a flow path for water, and then you join them to make one that looks like a monolith like this. But it's more to do. In order to make this cheap, you need high volume manufacturing. You need to put this into the same type of manufacturing operation that makes light bulbs or pop cans or something at a high rate. Once you do that, these will become much more commonplace and much less expensive. The prediction is that it'll be this type of cell with PEM proton or polymer exchange membrane, because it in high production is going to be the lightest weight system and use the least amount of Earth's resources to produce it.
What did you say that material is made out of?
Well, it's perfluoroalkoxy, modified to have sulfonic pathways for conduction. It's like Teflon. You want the water to think that membrane is Teflon. And you want it to be like Teflon in temperature capabilities. And you want the electrons to think it's Teflon. You want the electron to think, man, that's a really good insulator. You want the water to go away from it, wherever it contacts it, or beads on it. It looks like water on a duck's back. And you want it to stand temperature, so you can put a lot of current through it when your car is fully loaded and you're going up a hill. And you don't want it to melt down.
Will Teflon ever work in systems like that? I mean, it's probably not a porous.
You build it out of Teflon powder, and you build into it the pathways for ion exchange, and you fuse it to make it impermeable to the gases. or you build it out of a solvent that precipitates the film, and you evaporate the solvent and recover it.
Are all fuel cells exothermic?
No. That's a very good question. We could conceive out of the periodic chart fuel cells that are endothermic. We could. But all the practical ones are going to be exothermic. The practical ones will be exothermic. But you could make a thermally regenerative system that was endothermic. Yeah, you could build a redox cell. But it is interesting, and I think that the question you bring up is a really important one. The reactions that we want to run are exothermic. That's for sure. And we're probably going to make compromises one after another, that wind up at about a 30 or 40% overall efficiency, which means that they're always going to have heat for your cogeneration loads. You know, we could conjure up some exceptions, but that's the practical world we live in. If you're going to burn natural gas, it's going to be exothermic. If you're going to burn fuel oil, it's going to be exothermic. If you're going to burn hydrogen in your fuel cell, it's going to be exothermic.
Is it Nafion? What's used in most of these fuel cells?
Nafion is one of the oldest and still most popular membranes. It's supplied by DuPont, and it's an example of a Teflon that's been modified for making it into a semi-permeable membrane. You can also buy it out as electrodialysis membrane.
Now, guys like Ballard and H-Power, what's the difference between their fuel cells and where are they going with their fuel cells?
Well, Ballard has been using Dow membrane, which is a somewhat more conductive membrane than Nafion. And in order to get the price down, they've reached the decision that they should be producing their own membrane. And so they've separated from Dow apparently in that regard, and they are planning to produce quantities, or at least transfer the technology for producing quantities of membrane that is a partially fluorinated polymer that has a lower price than Nafion or Dow membrane. Basically, these membranes look like this on a MER basis. If you had traditional Teflon, well, you'd fully fluorinate it and repeat this cell. But that turns out to be a difficult one to put into solvents. And so you tend to make a perfluoroalkoxy, a more complex form of this, and to not fully fluorinate it. You may have a different structure where it's partially fluorinated like this. It becomes a more solvent susceptible material, so that you can mix this substance with carbon black and very finely divided platinum. Deposit it from a solvent so you get a very thin layer of material that has the properties of divorcing water, rejecting electrons, but readily accepting the ion that you want to produce in your fuel operation, in your fuel ionization and ion entry into the semi-permeable membrane. So that's a very good thing to do. That's one area that Ballard and Deus and others are working on. H-Power started with the phosphoric acid technology. And let me give some credit to the phosphoric acid technologies. The oldest fuel cell starts in 1837 and gets published in 1839. It's a sulfuric acid fuel cell. You can see something like what it was in the picture, in the diagram that's drawn on the bottom of page 143. This is a catch-all example of a lot of fuel cells that can be named, but the first one, Grove's first one, he published in 1839, used hydrogen within a porous platinum electrode, and used oxygen within a porous platinum electrode for the cathode, and used sulfuric acid as the electrolyte. The important discovery that he made, and he had the good sense to observe, was that this is a reversible cell. You could run a voltage on it and produce hydrogen from water, the water content of the sulfuric acid, or you could run it the other way just as well and produce electricity from hydrogen and oxygen. Extremely good power of observation, good science, and at the time he realized that this was a very valuable pollution-free answer to the killer fogs that were produced in London and other emerging production centers for the Industrial Revolution. But no one invested in it in a sufficient magnitude to allow these to become a cost-effective answer, even though he realized it was a direction that we should go in technology.
And what year was this?
1839.
Amazing. Absolutely amazing.
It is amazing. Grove.
Are there many types of membrane, all different sizes and types, but they're all home built though? There's nothing available from any manufacturers?
Oh no, Nafion is produced in.
Pardon me?
Nafion is produced in semi-production quantities.
No, you just put them together when you put them in. Huh? But they're expensive though, aren't they, to get the big ones?
They are. This type of cell that you're seeing on the left-hand side of 143 is typical to a lot of other fuel cells after the time of Grove. It's typical to the circuit of a phosphoric acid. You just change that electrolyte to phosphoric acid and heat it up by some means to make it adequately conductive, and you've got a phosphoric acid cell. And you'd probably use the same catalyst as Grove did, platinum. At the temperature of 200 degrees C with phosphoric acid, you wouldn't have to use any other catalyst. If you cooled it down by changing the electrolyte, even to a polymer electrolyte, and you were wanting to use natural gas, you'd have to add other catalysts to work in chain reactions along with the platinum to keep from being poisoned. For instance, you'd add ruthenium. In the presence of platinum and ruthenium, you can stand some carbon monoxide. Even at room temperature, or better off, you'd be better off at 80 degrees C at the limit of a PEM. But mind you, I mean, here's the point to be made, that's adding more expense and more complication. So the fuel cell that has been most used, most commercially adapted and tried is the phosphoric acid. Going to 200 degrees C is a great advantage. It solves a lot of problems, but it's still going to use platinum at least as a catalyst, both on the anode and on the cathode.
Can you take this diagram that you've shown here and show how you would hold the catalyst?
Well, the way you get the catalyst where you want it and not have much in inventory is this trick. There are several tricks. One is that you put the catalyst in ink, and you use either silk screen or laser printing techniques, it's the truth, to get a little bit, you're looking at dot type additions, a little bit where you hope you'll have this three-phase function. The three phases that you're trying to have come to common functionality are the gaseous hydrogen, that's one phase. The solid path for the electrons, another phase of the ensemble of stuff that you have available. And you have to have the ion go somewhere. So that's the liquid phosphoric acid or whatever. So to answer your question, I'll put this on in another color to give the notion that it's there, but you use as little as you can possibly think of getting there. at just where the 3 phases are going to be. In this diagram, you wouldn't put any over here. Nothing happens. But you'd put them, you'd do your printing on your platinum loaded ink right where you thought something good was going to happen. And then you try it and arrange your pattern some more and do it again until you get a least amount of platinum doing the most amount of current development. I mean, that's the way it's done in the field, is by an iterative process.
Now, what about the electrolyte? How do you store your electrolyte?
Well, this electrolyte needs to be stored in a humidity-controlled system if you're using PEM.
Well, I was thinking on the phosphoric.
Oh, phosphoric acid. Well, you can just get phosphoric acid that's pretty pure from the manufacturer, and store it without contaminating it with oil or other things that are common to storage.
Well, one of the concerns many people bring up to me when I talk about the phos acid is that, boy, now you've got an acid here, and you've got hydrogen, and you've got an acid, and you have a bomb in front of this building? Is that what that's going to be? And then I explained to them that it actually has of a sponge. It's more of a sponge material that actually, if you shook it, you wouldn't get phosphoric acid out of it.
I think that there's one thing that we owe the public, and let's take the blame ourselves, is that there's all kinds of myths that continue to make resistance, social resistance, to improvements such as the fuel cell. One of them is exactly what you said. It sounds bad because it's an acid. It sounds bad because the Hindenburg is associated with the badness of hydrogen.
Your car has about 200-degree sulfuric acid in it. It has windshield washer fluid that burns. It has things internally that will combust and produce toxic gases like the nylon in the seats and the foam. It's got a fuel tank full of a liquid fuel that will spread and burn quite readily as well, not to mention the rubber of the tires.
That's safe.
And got that behind the wheel.
Yeah, you got to get
Well, there's...
Also, I've had criticism because we were going to be putting out oxygen depleted air.
Oh, I've heard this too.
What's that?
It's an interesting thing. There's another myth that goes along the lines that if you run these fuel cells, you're going to ruin the air for all of us because the oxygen is going to disappear.
You put out oxygen depleted air because you're actually consuming oxygen from the air in this process.
Another myth is you're going to make life miserable because you're going to put so much humidity in the air.
Can't do both.
Well, okay, but here's the deal, and this is an important observation. If you run a fuel cell, for instance, at 30% efficiency, that's a noble thing to do, and produce the humidity from natural gas that it requires, and you compare that, for instance, with a 25% gas turbine, you've reduced the humidity to the atmosphere on the same fuel, same fossil fuel. But if you run your fuel cell on renewable hydrogen that you get out of dehydrogenation of garbage and sewage, or out of electrolysis using wind power or hydro power or some other source that didn't produce carbon dioxide, you'll have made water from water and have zero impact on the present inventory. Zero. Both ways you win. Both times it's a better answer. On the oxygen issue, this is also a better answer, because however you're analyzing the oxygen consumed, this is less than the gas turbine would have consumed. It's or internal combustion, whatever that other approach would have been. This one can be less. In terms of other resources of the earth, and the phosphoric acid as an example, the phosphoric acid doesn't disappear. You're not going to have carloads of phosphoric acid coming to the plant. This is a one-time inventory of platinum, phosphoric acid, carbon plates, or whatever plate the system runs on.
In other words, you don't have to, it's not going to use any of that up?
No.
It's just a one-time loading factor?
It's a one-time loading factor, and it's very susceptible to taking it all apart and recycling it. This one recycles very nicely.
Now, one to Fossasset, you do have to change out the stacks about every 7 years.
But
6 to 7 years.
but even so that you've changed them, they are recoverable. The platinum is still there. It may be blinded, but it's still there.
In the PEM
Arrangement.
bill,
Yep.
no, not the PEM, so the hydrolyzer that you've got back here that Hamilton makes. What are the problems with impurities in water and air?
The
Water going into it, not water in it.
yeah, that particular unit has within it a reverse osmosis cleanup of the water. And it's been of a style of being able, it's done that way because it's been of a style that was rated for use of seawater. The idea being if you're in a submarine, use your surrounding environment as your hydrogen source and as your oxygen source. So you run what you have plenty of, which is seawater, and waste some in reverse osmosis. Glad to waste seawater. And and you start with DI quality water in your makeup water for your electrolysis.
I just wondered about that unit I just saw, that water, a water tap connection there, and I just,
What they do with the hydrogen on sub? Outgas it?
It's still a national secret. It's still a national.
well, Ballard is building some submarine, fuel cell powered submarine.
Fuel cell powered submarines has come in a big way. Think of it. If you want to run silently, this is a much better deal than running a bubbler that produces steam. Producing steam is noise for sure. Oh, a boiler.
Nuclear.
Nuclear.
Yeah, pumps and everything else.
So what they would do is just carry a storage of hydrogen, run through the fuel cell, and drink pure drinking water while it's down there.
That's right.
Well,
Typically.
Let's have a nuclear reactor on board and just shut it off when we want to run silently. But we are in an area, turn the thing on, electrolyze, create it, and switch it back through.
Typically, these are silent running gear out of a primary power supply, which is nuclear.
Yeah, you got surplus electricity on board, that's for sure.
By the way, Roy, you won't find any mothball submarines with that thing still on it.
Oh, I wish we had a different story to tell you. We tried. They're still kept pretty close track of by the naval and other military authorities. Question?
Yeah, the argument is raised that if you have millions of hydrogen cars running around, you're creating a water vapor issue, which water vapor is a greenhouse gas, right?
It's absolutely insignificant compared to the amount of evaporation you get from the ocean, sun, and everything else.
Well, that's true, but you know, you have to, in order to convince somebody, you have to do this with them. You have to go through the analysis. If you burn 1 gallon of gasoline, you get 1 condensable gallon of water. And that's water that's come from 100 million years ago. You actually are producing from 100 million years ago in the surface inventory of the earth, in your town, in your yard, something that came from 100 million years ago. So you're bringing up and turning loose dinosaur fumes, or however you want to say it.
We're drinking the same water the dinosaurs drank.
Well, you're getting it back 100 million years delayed.
You're not drinking this.
But you're getting it back 100 million years delayed. Compare that to taking water out of the tap, electrolyzing it, making hydrogen and oxygen, recombining the hydrogen and oxygen for a 0 impact on the water. That's right. There's no water gain out of that. It's a null in the water accounting. So you get much less humidity out of the hydrogen economy than we have had out of the fossil economy. Rounded up from 8.33 to 9 pounds. 9 pounds of water will give 1 pound hydrogen. and 8 pounds oxygen. 1 pound of hydrogen has a higher heating value, taking it all the way to liquid water, of about 61,000 and a few more BTUs. 2 pounds of hydrogen are the same as a gallon of gasoline. Thus, in round numbers, 18 pounds of water will give you the energy units of a gallon of gasoline.
So about 120,000 BTUs.
Round numbers. Sometimes gasoline is more and sometimes it's less, but round numbers. Gasoline is 1,000 or so different molecules, acceptable molecules.
We have to have something like double the efficiency of the fuel cell to equal almost the energy of gasoline.
Well, if you did have a fuel cell that was running at twice the efficiency of a heat engine, you could get enough BTUs out of the hydrogen produced by electrolysis of 1 gallon of water to run the same range as the gallon of gasoline. That's correct. Yeah, by rule of thumb, and again, you know, we absolutely admit it that piston engines can be more efficient, but the way they've been running, they're about half the efficiency of fuel cells the way they've been running. Those are round numbers, but we give credit where it's due. The piston people can go a long ways. We're going to meet a man tomorrow that's already shown on a bench test that he can set a new world's record in a piston engine.
What happened to the deal that John Deere and Bluebird or somebody came out with here a year or two ago about an MEV catalytic radiator, or what was it?
Oh, well, those are two different topics.
Are they? I thought they were combined.
Well,
I thought they were going to run this through a catalytic radiator and then burn natural gas and come up with a 1.97 MeV or something like that.
well, in our glossary, we probably need to put in MEV and define our MEV, meaning minus emissions vehicle. To get a minus emissions vehicle, here's what you can do. You can do just what that suggestion implied. You can put catalysts on your radiator or catalysts on your muffler on the outside, so that any air that runs into them that is containing carbon monoxide, for instance, can be broken into, or we will produce, carbon dioxide instead. And any hydrocarbons that run into it can be converted to carbon dioxide and water vapor. And ostensibly, any oxides of nitrogen could be converted to nitrogen and oxygen. But the rate at which that MEV shifts unwanted things in the air to acceptable things in the air is minuscule. It's just minuscule compared to putting hydrogen in a piston engine. There's hardly any approach that cleans the air faster than just putting hydrogen in a piston engine.
Just with ambient air.
Sure. Ambient air into piston engines is a great opportunity for quick cleaning of the air. Engines breathe a lot of air. They bring the temperature to a very high peak instantaneous temperature at which the reactions proceed very rapidly. Much more rapidly than you can get on the radiator or the muffler of a car.
Well, I can tell you, there's basically not much airflow around the muffler. At 60 miles an hour, no, hardly any airflow around the muffler. At 60 miles an hour, take a vehicle like a van, you put a clear glass floor in it, and you put streamers down there. The streamers, the vehicle going 60 miles an hour going like this.
Yeah.
There's no airflow around the muffler.
However,
It's a couple feet per second.
if you put it on the radiator, it's like 8 times the amount that you would actually take into the internal combustion engine.
It is that, but the temperature is so much lower that the rate at which it is changing or converting is about 1,000 times less.
Yeah, I mean,
Turns out to be way downscale.
Mechanisms like electrostatic, to remove particulate matter and
That has greater hope. Anytime that you can get particulates out in modern air, it's of great use, and electrostatics are very efficient in separating air and particles, gaseous molecules and particles. Please.
You've got a couple other really negative impacts of the internal combustion engine, and that is the oil used in it. Every year 200 to 400 million gallons of oil gets dumped into waterways.
Absolutely.
And all that, and down into groundwater situations.
Yep.
Plus you have the noise.
Yeah. Absolutely.
Eliminate those two things would be an incredible boom to the
You
environment.
don't want to get rid of the engine noise. You don't. You'll start hearing the driveline noise, and the wheel noise, and the wind noise. You don't want to get rid of the engine noise.
Jake brakes coming down to-
Yeah, the Jake brakes. We need a lot of Jake brakes.
Yeah.
Drag race.
Yeah, we do.
Okay.
It's really a serious joke. Once we get rid of the wind noise in the vehicle, well, then people start complaining about wheel noise and driveline noise. And
Everything else is silent.
right. How do you fix vehicle noise? You put it in a CD player for it.
There's an extremely important point that is made with the fuel cell equipment. It does show up noise from other sources. You start really paying attention to other sources. It's very true.
Vibration.
Well, sure. Finally, you get around to the tires being a major producer. Tires themselves.
I've heard that comment from all electric cars.
Chasing noise in a transportation device, whether it's an airplane or automobile or motor scooter or bicycle, turns out to be a major issue. They're converting a lot of energy to noise.
Who besides Ballard right now is the major player in the fuel cell?
Well, Ballard has licensed some major players. Ballard sees themselves principally as a technology development company, engineering.
They don't want to be the manufacturer.
They license
That's what
others,
they're tied up with.
Ford and Benz.
Mercedes.
That's right. Other major players were mentioned. H-Power. They have good phosphoric acid technology. They're trying to get into PEM technology.
Weren't they the ones that were talking about the iron oxide?
They were.
nitrogen products?
They were. Energy Partners in Florida are a major producer of PEM type fuel cells. They're a good technology company.
Is that listed in the back of these?
You'll find it in the back of the green handout.
Are they a public-owned company or are they private?
Ballard is public. Energy Partners are semi.
Semi.
They're not public to anybody but sophisticated investors. The last I
They're a limited partnership.
Yes.
How about H-Power?
H-Power is trying to be public.
They are trying.
I don't know what stage they are in at the moment, but they're trying to be public. Deus is trying to be public.
Who?
Deus, D-A-I-S.
Never heard of
They're a
AS?
small company.
No, D-I-A.
Oh, excuse me.
D as in David.
Yeah, David.
Make my hearing go back.
Excuse me. Another one is Urgenics. They're an offshoot. They were, by and large, personnel with International Nickel previous to forming up as Urgenics.
International Fuel Cells is another one. They make the ONSI, that's the unit that we purchased.
International Fuel Cells.
Pardon me?
Are they out of Florida?
No, they're out of South Windsor, Connecticut. They have beautiful plant.
I just read the other day in Popular Science or Mechanics or something that some company in Florida just shipped their 200 unit.
Well, ONSI has produced more than anyone.
Yeah, ONSI is producing. And there's 70.
I just read this little deal.
That's got to be them. That's got to be them.
It's out in Central Florida.
United Technologies has more fuel cell ventures than anyone. They have
That's Hamilton Standard.
the Hamilton Standard type of devices. They have ONSI and International Fuel Cells. And they all meet somewhat different markets.
Yeah, United Technologies, I think, builds those on the space shuttle.
They do, through Hamilton Standard.
And then the ONSI is the stationary 200 kilowatt units.
And they have the records. Let me just mention them. The phosphoric acid holds the records for longest in the field, longest up, and are actually the closest thing to a non-interruptible power supply that's available to the industry. They're much more likely to be operative in an extended period analysis than gas turbines. Much more likely to be up than a steam turbine plant or a nuclear power plant. So if you have
Are they a 1,000 degree operating deal or are they the intermediate?
200,
They're intermediate.
get the, you can get 250. We ordered the unit that it gives us 250 off because we wanted the high
Heat.
efficient. Well, I forget what they call it.
Speak a little louder.
They wanted to get a higher quality heat, and it didn't make much difference in efficiency at all. The voltage difference is very small. In fact,
250 degree heat coming off of it. 250 degree water is what comes off of our unit, and then we use it for heating up water in the building, and then also.
B250C.
No,
no.
250. Yeah.
His water could be steam, though. He can get low-quality steam.
Agreed. How do you keep it from being steam?
Just pressure.
That much pressure.
Not that much. Your car radiator
Pretty
runs.
much.
Your car radiator runs that high.
Yeah, most cars are maintained at pressure
You're talking about
sufficient
steam.
to.
No. Yeah.
250 degrees.
After 200.
Well-
212, you'll have steam at atmospheric pressures. So at like 20 pounds, you're still going to.
But ONSI can deliver even higher temperature steam if you have an application that requires it. They'll help you get it.
Well, that sounds almost identical to what we use.
Well, that's why I was
Steam cooking.
That's why I was looking at you, saying that, you know, for your list of things you wanted to find, there's a pretty close fit.
I've got a sales manual here, not that I sell those things, but
I'd sure be appreciative. I'd like
Yeah,
to try to get a copy of it or something. Just
I don't mind giving them a plug in the sense that, you know, we'll identify it as a recommendation because it's a product that is worthy of recommendation.
I don't know about that.
Okay, well, let's take a break while Walter looks at that. I'd like to